Good afternoon, everybody. Welcome to our webinar for the month of February. My name is Hugh Daigle, and I'm the director of the Center for Subsurface Energy and the Environment here at the University of Texas at Austin. A little bit of background about our center. We are a group of 27 researchers here at UT who do work on all aspects of subsurface and environmental energy science. We have a broad range of research topics that we work in, including conventional oil and gas, but also we do a lot of other things too, including unconventionals, carbon capture, utilization, and storage, working on methane emissions, geothermal energy, gas hydrates, to name a few. Our researchers span a broad range of technical disciplines, including reservoir engineering, which is very strong, but also petrophysics, things like conventional geology, sustainability, data analytics, machine learning. You can get a flavor for that here from this diagram. And the tools we use for investigation include things like experiments at both large and small scale, simulations, both at very large and very small scales, and software development and other types of engineering tools. Much of our research gets done through our industrial affiliate programs, which are ways we have of interfacing industry with the research that goes on here at UT within the center. This is a listing of the different industrial affiliate programs that we currently have that are active. If you want more information on these, I suggest that you go to our website where you can find more info and also contact information for the directors of these IAPs. A little bit about our monthly webinars. We have monthly webinars on the second Tuesday of each month. They're intended to be ways of getting the research that we do here at the center out to you all in industry or national labs or other academic institutions to broaden the scope and reach of what we do here. They're on the second Tuesday of each month at noon U.S. Central Time, and they're held on Teams. And if you miss a webinar, we always upload them to our YouTube channel. So I suggest you go there and check it out, subscribe. You can see all our past webinars. Here are a few snapshots of ones that we've had recently. A little bit about our upcoming webinars. We're not going to have one in March because all y'all down in Houston are going to be on spring break, but stay tuned for information about our April and May webinars. A little bit about our sponsorship opportunities. We offer sponsorships for our webinars at a level of $5,000 per webinar. If your organization is interested in this, we would put your name and logo prominently at the webinar flyer and also the beginning and ending of the webinar. And you would get access to our live audience, which includes industry, government, and other academics. We publicize these webinars both publicly and privately and put them up on YouTube after the live event, where we've had over 10,000, actually over 14,000 views in the last 2 years. So for you, as a webinar sponsor, you reach a global targeted audience. You associate yourselves with the wonderful high-quality work that we do here at the center, and you help support the center's mission of advancing research and education in subsurface energy and the environment. So for more information on this, you can contact me. There's my email address, Daigle@Austin, for more information. So now, without further ado, let's move on to today's webinar. So a little bit of housekeeping before we start. If you have questions during the webinar, please type them into the Q&A section. We will get to those at the end of the webinar, but you can just type them in as they occur, and we'll get to those. And again, if you have to step out or want to go back and rewatch the webinar, we'll put this up to the YouTube channel within a few days. So now it is my pleasure to introduce today's webinar speaker, Professor Hui Tang, who is a new addition to the university. She started with us back at the beginning of fall semester. And she'll be talking about deep learning accelerated forecasting in geological carbon storage. Dr. Tang is an assistant professor here at UT, and prior to joining us, she was a staff scientist at Lawrence Livermore National Lab. She has a PhD from Texas A&M and postdoc at Rice and LLNL, and has already a very distinguished record of publication and research on subsurface processes, including deep learning, which she'll be talking about today. So with that, I'm going to hand it over to Dr. Tang.
Okay, thank you for the introduction from Dr. Daigle. Hello, everyone. It's my pleasure today to introduce you some of my work on deep learning accelerated forecasting in geological carbon storage. And the work was mainly done at Lawrence Livermore National Lab with my previous colleagues, Joe Morris, Qingkai Kong, Chris Sherman, and Pengcheng Fu. We also have some really brilliant summer intern students has helped with the work, such as Honggen Zhou, which was previous PGE graduate students, and now assistant professor in Korea, and Su Jiang, which was previously a PhD in Stanford, and now a postdoc in Berkeley National Lab. And the effort was funded by DOE SMART initiative. So this is a DOE program that focusing on developing science-informed machine learning tools to accelerate real-time decision makings in subsurface applications, and specifically for geological carbon storage. I have involved in several tasks in SMART initiative, and one of the major goals is to use machine learning tools to accelerate the history matching for reservoir model calibration. So imagine that we start with a geological model that has been constrained by static data, such as seismic well logs, cold data, and then we can discretize this geological model into grid blocks and input it and to build a reservoir model and input it to reservoir simulator or fluid flow model to forecast the reservoir performance under different operation strategies. However, there are a lot of uncertainties in such a reservoir model, such as we do not know what the porosity and permeability are distributed in such a reservoir model, and we may not know relative permeability curves. So to reduce these uncertainties, we can collect history data and try to match our model predictions with this history data. And this process is called history matching. And typically in industry, it's not uncommon for a reservoir engineer to spend months to get a reservoir model history matched. However, in energy transition applications such as geological carbon storage or deep water oil and gas development, this can be even harder since we are facing much larger uncertainties due to the drilling cost is high. We do not have that much wells to constrain our reservoir models. And also we want to speed up this history matching process as fast as possible, to make it as fast as possible so that we can reduce the cost. So the major objective for us is to develop near or real-time history matching workflows that can handle larger uncertainties. So how could we do this? So here, to build an automatic history matching workflow has been studied for decades, and we can view it as a process where, as an optimization process where we update our parameter space to reduce the mismatch between prediction data and observation data. And then with the calibrated model, we can further do performance forecasting. To account for the uncertainty in the parameter space, we need to invite some concept of Bayesian inference. And here in this presentation, I will mainly use two concepts of Bayesian inference. One is prior models, which means the initial guess of reservoir models, and also posterior models, which are calibrated reservoir models that conditioned to observation data. And how can machine learning or deep learning help in such a history matching workflow? So first, it can help with model parameterization. So our initial guess of reservoir models are usually contains of facies, permeability, or porosity distributions that discretized in in grids or cells, and there are usually thousands or millions of them. And it's a large parameter space for us to update and for us to history match for. So the first step we usually do in reservoir history matching is to reduce the dimension of such a reservoir model and to represent with a much smaller parameter space. And this process is also called parameterization. Traditionally, we can conduct parameterization with some dimension reduction methods such as PCA, principal component analysis. However, PCA has its limitation to restrict in mainly Gaussian field, and we can leverage machine learning models to parameterize more complicated field with methods such as CNN PCA or GAN or VAE. And the second part of this history matching workflow that can be helped by a machine learning model is this high fidelity forward model component. And this is the most computational intense component in this workflow since it needs to be run thousands of times. So if we can build a machine learning based surrogate model for high fidelity forward model, then it will dramatically increase the computational efficiency of this workflow. And to build machine learning based surrogate for this kind of PDE solvers have been a really hot research topic in machine learning field, which is called scientific machine learning. And we will dive into it further. Here, I want to go back to my observation data. So in terms of observation data, traditionally in petroleum field, we usually use the pressure, bottom hole pressure, or injection or production rate as our observation data for history matching. However, for carbon storage applications, we usually do not have that many wells being drilled due to high drilling cost, and the pressure obtained from this injection or monitoring well are usually sparse and cannot be a sufficient constraint of the reservoir. So we are thinking whether we can use more INSAR as low-cost, high-dimensional monitoring data. Here, INSAR stands for Interferometric Synthetic Aperture Radar, and it has high-quality data freely available every one pass every couple of weeks, and it can give millimeter resolution for deformation. So here we have some freely available high-dimensional data, and we also have the capability to simulate the surface deformation through coupled flow and mechanics. So we can, starting from a permeability or porosity realization, we can simulate pressure from Joule's X and then build a geomechanical model to all the way to the Earth's surface and then model the surface deformation. And it's a one-way coupling process. So here I will use an example to demonstrate this, whether we can use INSAR data to calibrate reservoir model and to predict for future reservoir performance using a synthetic dedicated CO2 storage case that is commercial scale. So it considers a commercial scale injection scenario of 2 million metric tons of CO2 per year injection across 4 wells at fixed locations for 10 years. And here we also consider a relative complex geological model where there are 2 fishes. One is sandy fishes represented by red, and the other is shaly sand fishes represented by green. And we also have porosity and permeability distributions as our reference reservoir models. Here I show some statistics of this reference model, and we have porosity and permeability followed by model distributions, since we have different distribution in sandy fish and shelly sand fish. And also, we have no simple one-to-one correlation between porosity permeability. However, they are kind of dependent. So it's give us some difficulty to build the initial reservoir model. And our goal is to test our hypothesis that whether it is feasible to use INSAR inverted surface displacement as observation data to infer and forecast reservoir pressure distribution. So here we use this synthetic vertical surface displacement data as our observation data, and it is from the surface displacement at 2 years added with 5% Gaussian white noise. And also, we want to forecast for our reservoir pressure for 2 years, 5 years, and 10 years. So to achieve this goal, we build such a 3D workflow using INSAR data to infer for reservoir pressure. And this workflow mainly contains three components: model parameterization, data assimilation, and performance forecasting. So I will not go to details of every component of this workflow, but I will mainly focusing on the machine learning components in this workflow. And for details of each component, you can refer to this publication. So for the model parameterization part, our goal is that from this initial reservoir model, like we have fishes distribution, porosity distribution, and permeability distribution discretized in thousands of grid blocks, can we find a latent space to efficiently represent these initial reservoir models? And also from this latent space, can we generate new models? So these new realizations of fishes distribution, porosity distribution, and permeability distribution. So here is our major objective of doing model parameterization. So what if the first thing what we try is that what if we use traditional PCA-based method? As we know that PCA can only is mainly applicable to Gaussian distributed field. However, here for fishes realization, it's really a binary distribution. And if we reduce the dimension of this fishes realizations, and then if get a latent space variable representation and try to regenerate this field with PCA, this is what we get. So it is a continuous distribution. So how could we solve these difficulties? We adopt a model transform net based on CNN. So through this model transform net, we can process these PCA generated realizations and then convert it to some binary realizations that much similar to the original fishes realizations. So in this way, we can use the original latent space founded by PCA to generate new fishes realizations. So here, this is our first step. We use a 290 dimension latent variable to generate fishes PCA realization and then apply a model transform net to get a CNN PCA realization. And then for the porosity and permeability realizations, we just apply the traditional PCA approach. And so we first normalize the porosity and permeability to build the PCA matrix. And then we find the latent variable that can preserve the a reasonable amount of variation. We find it to be 600 something, and we perform PCA to generate normalized porosity and permeability. Okay, and then we do a cookie cutter approach to rescale the porosity permeability based on fishes and to get the final porosity and permeability realizations. So in this through the CNN PCA approach and combined with conventional PCA approach, we can really easily reduce the original parameter space of these three realizations: fishes, porosity, permeability. Reduce this parameter space from 110,000 to 1,000. So now we can come to the second step. We now have a Latin space that can represent our field, like fishes, porosity, permeability field. And then the next step is like we want to find a deep learning surrogate model that can surrogate for our forward simulator and to predict for the surface displacement. So we start with a UNIT-based model and modified it a little bit to a 3D to 2D residual UNIT architecture. And here we input porosity field, 3D porosity, permeability, and time field. And through this reduced mean concatenation, we can directly predict for the surface displacement at different time steps. Here is our data generation for surrogate model training. We generated 7,000 porosity permeability fields from the two-step CNN PCA methods that we have introduced. And then we run high-fidelity flow and geomechanics simulation with geos. There are 6 overburden layers and 1 basement layer being considered with fixed porosity properties. And then we evaluate for different sizes of training reservoir models of 1K, 3K, 4.5K, and 6K. And we find that when we evaluate the accuracy of these different models trained by different amount of training data set, we evaluate its accuracy based on RMSE and R-square. And we find that we do need around 6,000 of training data to achieve a good accuracy. And so we can achieve with 6,000 training data, we can achieve accuracy of R-square larger than 0.985 for this placement model. And as well as we need this much training data, like 6,000 training data, to achieve a good accuracy for this pressure model as well. With this surrogate model in hand, we then plug it into a history matching workflow. And the history matching engine we use is called ESMDA. So the process is like we compare our predicted surface displacement with the INSAR interpreted observation displacement and compute the mismatch between these two, and then try to update our latent parameter space that's generated by CNN and PCA. And through ESMDA is represents for ensemble smoother multiple data assimilation, and it has been really a wide adopted method for history matching in the industry. And the main idea is to perturb the observation data with random noise for several iterations so that we can update the parameters for several iterations. And here we have 100 ESMDA ensemble and 12 iterations to update our initial guess of parameter space, to update this M vector. So here I show some results of the prior realizations of the reservoir model. So this is my prior guesses of reservoir model, and also the posterior realizations after assimilate the observation data. and how it compares with my reference reservoir model. So since this is a large model with larger uncertainty, we cannot expect that the post-realization to be really similar to reference, but it does change toward the reference. So it's more like the reference than prior do. And we can further test this by calculating the prior mean and standard deviation, and as well as posterior mean and posterior standard deviation. And we can find that this posterior model is much like the reference than prior in terms of where high permeability region located and where low permeability region located. And here is our surface displacement prediction based on the prior reservoir model and the posterior reservoir model. So in the first column, I show the prior prediction mean and standard deviation, and it's basically a no best surface displacement among all four injectors. And for the posterior, we have now more displacement around these top two wells, and it's very like our true observation data, since we have updated our parameter space to make it like our observation data. And here I show the depth average, the pressure forecasting for 2-year, 5-year, and 10-year. And here on the first row, I show the true pressure distribution from the simulation. And in the second and third row, I show the mean and standard deviation of pressure distribution. So we can see that by assimilating the surface displacement data at 2 years, we can have a great pressure forecasting at 2 years and with less uncertainties. And also, we can have a good prediction on pressure at 5 years and 10 years as well. Here, I summarize the computational cost. The whole workflow completes within 30 minutes on a 4-core personal computer. Well, if we use a traditional workflow with reservoir simulators, it can cost around 3,000 CPU hours. Well, this significant computational cost reduction is rely on deep learning-based surrogate models. So here I summarize the single run for pressure and displacement will take for physical simulator and what will it take for deep learning-based surrogate models. And also I summarize the training data set cost here. So we need to admit that all the computational efficiency that has been achieved by this history matching workflow is due to that we have generated a really large training data set to train for a surrogate model. Well, in many cases, we may not affordable. It might not be affordable to generate such a large training data set. And so the question to us is that whether we can reduce this training data set cost through model perspective and through training perspective. So this also brings us to the second part of this talk, where I want to focus on how we could propose a new training technology to reduce the training data cost. So in terms of data-driven deep learning models, we have seen a lot of successful cases based on convolutional neural networks. So the key idea is to reformulate the problem as an image-to-image regression task. And we have seen UNACT, peaks-to-peaks, and a lot of CNNs that is very good at this kind of task. However, the training data cost is really high. As I've shown in the previous case, I need 3,000 training data to get a reasonable, good, accurate models for pressure and displacement predictions. And So then recently there are another set of deep learning models being proposed. It's called neuron operators. And the key idea behind neuron operators is to learn this infinite functional space by learning the operators inside the PDE functions. And one of the most popular neuron operators in the literature is called this Fourier neuron operator. And this neural network structure was proposed by Caltech team in 2021. And the key idea is to map the input function to output function through these Fourier convolution operators. And these Fourier convolution operators mainly contain two passes. One is frequency pass and the other is real pass. So real pass is mainly do linear operations, while this frequency pass is doing Fourier transform of the input space and then do some linear transformation in Fourier space and then do inverse Fourier transforms to transform back to real domain and concatenate the output from real pass and then give the final output after activation. So why we think FNO is a better PDE or surrogate? Yes, since the PDEs, they are very different than real-world images. So real-world images, they have a lot of edges and shapes, and they are very good to be represented by the CNN-based by filters in CNN, and they can capture this real-world image edges and shapes well. However, for PDEs, we have inputs and outputs that mostly continuous functions, and it's more efficient to represent them in Fourier space and do global convolution. And the Fourier filters, they leverage these global sinusoidal functions, which are better for representing continuous functions. Also, another advantage specifically for this Fourier neuron operator is that parameters are learned directly in Fourier space. And so we can resolve the functions in physical space at any resolution. So here I show an example in its original publication where they train this Navier-Stokes equation based on a 64 times 64 data set on the first row, and then evaluate the model on a 256 data set on the second row. And we can see that although the model is trained on a really across discretized data set, it can predict well on a high resolution, finer discretization. And this is a very interesting property, and they call it zero-shot simple resolution. So from this property, we are thinking, okay, whether we can further reduce the training data cost by these neuron operators through multi-fidelity training. So what I mean by multi-fidelity training here, if we want to train the model first with a large amount of low fidelity data, and then fine-tune the model with a small amount of high fidelity data. And the FNO, since it has this resolution invariant property, it makes the transfer learning process much simplified. So in general, we just need to pre-train the model with low fidelity data and use it as the initial model to fine-tune for the high fidelity data without changing any model structure, since model is not discretization sensitive. And here I show a testing case where I have high fidelity input given by this 64 times 64 times 28 and low fidelity input given by this 62 times 62 times 28 and the porosity and permeability field discretization. So the first high fidelity input is the same case as I showed in the previous INSAR data history matching case. And we can find that what is different for our application in subsurface is that our simulation results are sensitive to the discretization. So if we are using high fidelity input, we will have much higher pressure around the wellbore than using low fidelity porosity and permeability as input. And also the CO2 saturation distribution will be slightly different as well. So that means if we directly train a model using this low fidelity input, then we directly train a model using this low fidelity input output, then we directly predict on high fidelity input, we can get some pressure and saturation output, but this is not accurate, or it has a lot of errors. So here at the first row of low fidelity model, I show the pressure RMSE and saturation RMSE if I use a low fidelity model trained based on 2,500 low fidelity data and directly predict on the high fidelity data set. So very error prone. So how could we mitigate this? We can fine tune this low fidelity model by some high fidelity data. And so here I try to fine tune it with 100 data, 300 and 500 high fidelity data. And we can find that amazingly, even with just 100 high fidelity data to fine-tune this model, we can get model predictions as accurate, almost as accurate as those high fidelity models that trained based on 2,500 high fidelity data. So there are two important takeaways in these results. First, remember that previously, when I apply a CNN-based residual U-net architecture, we need 6,000 high-fidelity data to get reasonable R-square to get reasonable accuracy. Well, here with neural operator model structure, we can reduce the data cost to 2,500 high-fidelity data to get reasonable good predictions. However, we can further reduce this data cost by using low fidelity data combined with a small amount of high fidelity data. And this is the major takeaway. So here I show the pressure prediction results. And at the first line, I show the simulation results, different realizations, and high fidelity high fidelity model results and the multi-fidelity model results. So I use those multi-fidelity models fine-tuned by 100 high fidelity data. And we can see that the predictions of high fidelity and multi-fidelity models are really similar. And it's even more obvious if we calculate the difference of the model predictions with true model predictions. And so they are within the same error range. And here I show the results of saturation predictions. And similarly, as at the first row, I show the simulation prediction results. And on the second and third row, I show the high fidelity model prediction results and the multi-fidelity model prediction results. So very good and accurate predictions. And if we calculate for area of review of the simulation, so area of review is calculated based on project these saturation plumes onto a single 2D plane and apply a certain threshold to get the area of review. So this basically tell you how your CO2 plume distributed in space. And then we can calculate the difference between high fidelity model and the true model in terms of area of review, as well as the multi-fidelity compared with true model in terms of area of review. And we can see that these two models can predict very similar results, so same accuracy. And here the results is some computational cost summary. So we leverage a data parallel training framework. So we can parallel the training on 8v100 GPUs. And for this multi-fidelity training, the total training GPU hours is 37 GPU hours, and the data cost is like 1,000 CPU core hours. And well, for high fidelity model, it's much higher. So we can in general see the multi-fidelity model has 80% less training data cost and 40% less training time cost. So it's a lot of computation resources saving, and it's a really interesting result. So here I'm summarizing this presentation. So I have introduced 3D deep learning assisted data assimilation workflow and demonstrated that the efficacy of using INSAR data as monitoring data to infer reservoir pressure. And this results has been published on International Journal of Greenhouse Gas Control in 2023. And for the second part of the presentation, I introduced the proposed a multi-fidelity FNO model to reduce the computational cost of generating training data sets while maintaining the same prediction accuracy. So here, the results has also been published in Journal of Hydrology last year. And here I only introduced the first really simple demo case of this multi-fidelity training framework. And in the paper, I have also elaborate on the generalizability of the model. So I have tried to say further stress test the model if, say, we introduce the model to a much larger reservoir domain and discretization. And I can show you this in Q&A as well. So here I want to introduce a little bit of the future work of my research group. First, we want to further advance the development and the adoption of scientific machine learning models for subsurface energy related applications, including coupled multiphysics process for structured or faulted domain. And here I have recruited very talented PhD students to work with CS professors to tune the foreign neural operator, to tune this model structure of foreign neural operator, and to try to make it adapt to multi-physics simulations. And also, we want to assimilate multi-model observation data. So it can be stream, temperature, acoustic, or chemical data from fiber optics monitoring or from other geophysics monitoring tools or seismic to improve subsurface property characterization and uncertainty quantification. And so I'm really open to collaborate with industrial partners in any of these topics or in general machine learning and deep learning related topics. And here's all my presentation, and I'm stopped here. Thanks for your attention. So here I have a question from Hongshen Wang. He says he is asking, thank you So he is asking a question about INSAR data. He asks, do you need any noise reduction or pre-processing steps for the INSAR signals? I mean, some other factors such as geological structure, rock types, or any other potential noise sources may affect the INSAR data. So do you need to extract the critical information regarding pressure change from INSAR data first? Okay, so here I want to ask, so there are two questions here. First is about pre-processing. Okay, so the pre-processing part, since we are doing a synthetic case, we are not doing synthetic pre-processing of raw INSAR data, but that's a very important step if we are dealing with raw INSAR data. And there are professors specifically focusing on this in UT. I think her name is Jimmy Chen, and in other department. So we have so we can collaborate with her if any collaborators have true INSAR data that you want to work on. And also, you talk about, do you need to extract the critical information regarding pressure change from INSAR data? So this is exactly what this workflow is demonstrated for. So we are actually extracting the embedded pressure information from INSAR from this history matching workflow. So we use the INSAR data or the INSAR interpreted displacement data to calibrate our reservoir model and then to further predict for pressure. But since INSAR, the deformation and pressure, they are highly correlated, so we demonstrate this is a feasible solution. So I got another question is, what are exactly matching parameters that you fitted with your AI models during history matching, which is not clear here? Okay, let me clarify it a little bit. So I can pull my slides out. So here is the workflow. So you can see like the parameter that actually being history matched is this latent space parameter. So this latent space parameter, how I get it? I get it from another AI-based model, machine learning-based model called CNN-PCA. So through this CNN-PCA model, I can use a latent space vector variable. So it's basically 290 plus 656 around 1000, a vector parameter to represent or to regenerate for porosity and phase realization. So what I'm doing is like a history match for this parameter vector. So this latent space vector, lambda n1 and lambda n2. And then after I update this parameter, I use this CNN-PCA approach to regenerate phase, porosity, and permeability distribution. And this distribution will be my input to my deep learning-based surrogate model, and for the following like observation data prediction and also for reservoir performance forecasting. Hope this answers your question. Yeah, there's a new how generating permeability field distributions by your deep learning models is different than conventional statistical models. What are the benefits of machine learning models exactly? Why you didn't use machine learning models? So how So first, I didn't really understand the second one, but I can answer the first one. So it's different than conventional. How it's different than conventional statistical model. So in conventional statistical model, we typically use, say, variogram-based models or those objective-based models to populate the geological realizations. And actually, in my workflow, let me share my screen again. So actually, in my workflow, for the initial reservoir model, population, I am also use the traditional geostatistical approach to generate this initial reservoir model guesses. However, I cannot directly use them for history matching because the parameter space is too large. So I need to parameterize them with a PCA-based approach or a AI-based approach to represent with a lower dimensional data and to fit in this history matching workflow. And these initial reservoir models, they are truly generated by traditional geostatistical models, and they are actually generated by GeoStatsPy, which is a Python package developed by Dr. Perch in our department. Out of my line of work, but question, are there limits to application of your method with regards inside data, like knowledge of the reservoir and structure of the reservoir? Yes, I need to admit that there are limitations to apply, especially inside data. So here, we only focusing on the uncertainties of porosity and permeability inside the reservoir. However, when we build the mechanical Earth model, we need to build a model from a reservoir layer and all the way up to Earth's surface. And all the mechanical properties of these layers in between surface and reservoir, they are actually uncertain. But here in our model, since it's just a preliminary study, we assume they are all constant variables. So we assume there are no uncertain there. We know them. But if we are dealing with true inside data, I think it will be really interesting to expand based on this workflow to study, okay, what the uncertainty of those layers in the middle, like what the uncertainty of mechanical properties of these middle layers like. And it will make the model even more insightful and more representative. In your deep learning network, the data to be compared is well pressure data and 3D seismic data. So I'm taking this question this way, so whether this workflow is applicable to, say, well pressure data and 3D seismic data. The answer is yes. So for well pressure data, it's pretty straightforward, and it has been done in industry a lot. So since well pressure, it can be a direct output from reservoir simulation, so we can predict this variable well, and we can compare it with our field measurements. And so it's really straightforward. For seismic data, it will be 3D seismic data. It will be really interesting. Actually, I have another work that I didn't present here, but it is a work before this INSAR data, this INSAR history matching work, and it's where I actually use seismic interpreted CO2 plume as my observation data to history match and calibrate a reservoir model, and then to do future predictions for reservoir performance. So seismic data can be really useful here for calibrate reservoir models. However, since we currently do not have a seismic model predictor, so we have to assume that we have already got CO2 plume that be interpreted by geophysicists through seismic data. However, if we can, say, collaborate with geophysicists, and they can use our simulation output CO2 plume and to generate seismic data, then we can complete this workflow by directly assimilate seismic data. So it will be really interesting, since it will be able to loop together everything we see the field, and we will have more comprehensive uncertainty analysis. I got a question saying, has the study been applied to a real field scenario? Yes, it is. And we actually, in the phase 2 of SMART, we applied the whole workflow to Illinois Indicator Project, IBDP, Illinois Basin Indicator Project, and we leveraged the real field data mirrored from there to calibrate reservoir model and to predict for pressure and to predict for CO2 plume. And also the SMART team was building tools to for this application.